All right, what's going on, class? Welcome to another lecture. I hope things have been going well. Oh, drop my pen. I hope things have been going well for you. Right now, we're about to get into a new chapter, chapter 6 for our particular textbook. And in chapter 6, we're going to talk about this notion of bending. Now, for those who know about my background, bridge design is something that I do and have had years of experience in. And when it comes to bridge design, I would say that 90% of what we design according to when we're designing beams or girders, or we're designing bridges for that matter, is bending moment. Let me show you this picture right here that the textbook has. It shows this bridge being constructed, and these are steel girders, right? These are actually steel, large steel beams that are being stretched out across these bents here, these piers right here in the middle. And when these beams are stretched out, what they experience as traffic goes across, even as its own weight, dead loads of these diaphragms here, is a force causing it to bend, right? Or at least causing it to experience a bending resistance, right? So this is what we're talking about when we're talking about bending. And more specifically, we're talking about bending of beams. So just to give you a quick definition, right? And this is just for the sake of you making sure that we're all on the same page. Beams are long, straight members loaded. In our case, they're loaded perpendicular to the longitudinal axis, All right, that's how we're going to define beams. So think about a long straight member here. When we have a pin support on one side and a roller support on the other side, that's called simply supported. And keeping in mind that perpendicular to its longitudinal axis, which is in this direction, it's going to be experiencing some loads. Here's some pictures here. Speaking of the different way that beams can be supported, we got simply supported right here. Again, as I just drew a pin and a roller here. We have a cantilever beam, which is fixed on one side and unsupported on the other side. That's called a cantilever. And then we have an overhanging beam. So this is similar to a simply supported beam where you have a pin, you have a roller, but you also have sort of a cantilever portion right here beyond the roller, Now, when it comes to designing for beams, when it comes for determining what type of beams we need, what we must do and what we must account for is you must know the variation of internal shear and moment, right? So we're talking about as you move along the length of a beam, we must be aware of how the shear is being experienced internally along the length and how the moment is being experienced along the length. That's what we must know. Now, in order to make sure we are on the same page again when it comes to this, we must start off with our sign convention. I shared this in a couple of videos ago. Let me spell it right. C-O-N-V-E-N-T-I-O-N. All right, sign convention. When we're talking about our beams here, we're going to be doing some cutting of these beams in order to analyze the internal shear moment. If you're cutting and you're showing the beam from the left side, then the shear is always going to be drawn down. That's V. And the moment should be drawn counterclockwise. If you're cutting from the other side, then the shear is going to be going up in this case. And the moment is going to be going clockwise. So keep that in mind. Do not lose track of the sign convention when we get into the process of analyzing these structures. Now, let me show you something really quick. This is something you may have picked up in statics, or maybe not. But when we look at ways that beams are loaded, right? One of the ways that you all are aware of now is that a beam can be uniformly, or the load on the beam could be uniformly distributed, right? Where you have a load that is uniformly distributed along the length of the beam. And we call this, we use a W, excuse me, to denote that. Well, I will have you know that when it comes to W, in terms of calculus, and this is mind blowing for me when I finally realized how calculus played a role, this is the derivative of how shear is experienced according to X along the length. So in other words, the derivative of shear, X being the position, with respect to X equals the distributed load W. So inversely, we can also easily say that shear is the integral, or the antiderivative, as we called it in calculus, of this distributed load. So if you were to take the antiderivative of W, let's just say that that is a number, what would we get? What would we get? Well, we would say, let's just give it a value here. Let's say that W is negative 200. All right, let's say that's negative 200 pounds per foot. Where if we were to take the antiderivative of that, V would be negative 200 X plus what? Plus C, or plus B, plus a constant at the end of the day. So what would the shear diagram look like? Well, the shear diagram would look like this. You have this pin side, you have this roller side. It would start up here, and it would go down linearly. That's exactly what that is, a linear decrease by 200. Right? That is the graph of the antiderivative of this uniformly distributed. So check this out, though. What is the antiderivative of the shear with respect to X? If you already guessed moment, then you are correct. You know exactly where I'm going. Moment is the antiderivative of shear. So if we were to draw this, or take the antiderivative of that, just from an equation standpoint, what would it be? Well, M would be equal to negative 200. We will raise the exponent of the X, right? And divide that by 2. Plus, we use the B, so we'll say B, add on the variable X to it, plus C. So instead of a linear distribution, the moment graph would look like this. A concave downward shape. That is the moment. That is the moment graph, the moment diagram. So moment is the antiderivative of shear. Shear is the antiderivative of the distributed load. And so I could say here that the derivative of shear is the distributed load, and then also the derivative of moment according to X is shear. Does that make sense? So they're all going to move on throughout each other, and it's going to be important for you to keep this relationship in mind, because that's how we're going to solve for things, not just in the immediate examples that we're going to show you, but in some problems and concepts moving forward. Now, let's take a look at some order of operations. I'm going to give you like a play-by-play procedure or some steps when it comes to solving for our shear moment diagram of beams. Order of operations is what we'll call this. All right, number one, excuse me, number one, find your reactions. Find your reactions. In other words, what is RA? What is RB? So forth and so on, right? So if we were to look at this particular beam right here on the screen, we want to know if this was A, what is the reaction at A? And what is the reaction at B? So that's step number one, find your reactions. Step number two, specify x coordinates. All right. At distances between concentrated loads moment couples or other discontinuities. Discontinuities. All right. And what I mean by that is, again, come back over here. If we're starting X from this side and we're drawing X from this side, well, we know that one segment of X is going to be right here. We're going to do one cut in this first part. Another X is going to travel past that reaction into this part. So this is kind of like a discontinuity, if you want to call it such. And if we were to have, let me show you, here's another one here. Boom, this is a perfect example, right? You have your reactions, you have some loads, you have some concentrated, you have a concentrated load, distributed load. What you're looking at here is different X coordinates. And these different X coordinates are going to determine different places where you could cut or where the equation of your shear and your moment internally is actually changing. So this is a good example of seeing what I mean when I say specify your X coordinates between things such as concentrated loads, moment couples, and discontinuities. All right, number three, everybody's favorite, right? Draw your free body diagram, FBD. Everybody knows what that means at this point. Draw your free body diagram. After you establish your final your reactions, establish your X coordinates, let's draw your free body diagram. After that, you're picking up steam, picking the momentum. What you should do is then solve for V, right? And, you know, by doing that, you're going to be basically some of the forces in the Y direction. Solve for V. And I'll say at cut or cuts. And then number 5, solve for M, your moment. And by doing that, obviously, you're going to be some of the moments about the cut. You're summing the moment about the cut. And then last but not least, after you've done this, you've gotten your values, you got what you need, you are going to plot your shear and moment diagrams. Now, I understand that sometimes you may come across something that's very simple. That's cool. If you know how to plot your shear moment diagrams without having to find the equations, how about you do it as a check? How about you make sure your equations give you the same thing that you intuitively know the free body diagram, or I mean the shear moment diagram will look like. But this is what we're going to do right now, right? We're going to get things going by looking at an example problem. I hope this makes sense to you. Coming back over here to the screen share, we're going to look at 6-5 right now. And I believe I have something here that will make it a little simpler for us to do on our document cam. Well, yes, I do. I have here a printout of what you see there on the screen, 6-5. So I can come over here to my document cam and you can see here, I think I got my light on, express the internal shear moment in the cantilever beam as a function of X, right? As a function of X, then draw the shear and moment diagrams. Straightforward, right? Well, let's go back to our order of operations. What was our order of operation? Number 1, we need to find your reactions. So right now we only have a 1 reaction because it's only fixed on the side. So this reaction is RA. There. So let's sum the forces about for the entire structure in the Y direction. So we got a negative 300. Then we have this triangular distributed load. So to do the triangular distributed load, we're going to do 1/2 base, which is 6, times the height, which is 200. Right? And then we have this lone reaction here at A, RA. So we'll say plus RA. Go ahead and isolate the unknown. And if you were to do that, 300 plus 5 times 6 times 200. The answer you should have is RA is equal to 900 pounds if your calculator concurs, right? So now we just did our first step. So now we know that RA is equal to 900 pounds. Number 2, specify coordinates at distances between things. So we're going to show our X coordinate just here. Now this distributed load goes across the entire thing. So we don't need to have multiple X coordinates. Also, this distributed load, or this concentrated load rather, is at the very end. So instead of saying X1, X2, X3, and so on, we're just going to stop there with X. And then what we will also do is from there, draw a free body diagram of a cut right here. All right, so here's what that would look like. So a free body diagram with that cut. Obviously still have our 300 here. Here's where we cut it. Boom. Need to cut it. All right. And then you got your V going down here. Boom. And then you have your counterclockwise moment there. Boom. And we don't have our entire distributed load, but let's see if you all can help me figure out what this value here would be. All right. So we know that this is a triangular distributed load. We know that this length here is some value X. So we're just going to do X. So the same thing we did here where we said 1/2 base. So 1/2 base, which is X over 2, right? 1/2 base times height. Well, what is the height? We don't know what the height is. It's not 200 as it has at the very end, but it's some ratio of whatever X is over 6, whatever that ratio is, times 200 is what this particular value is. So 1/2 base times height. Height is X over 6 times 200 to get that ratio. Hope that makes sense to you. And so from there, now we know what this value is. And we're going to use that to first and foremost solve for V as our order of operation tells us. So sum the forces in the Y direction, and keep in mind that this is for the cut now. So let me put that here just so we can know what we're working on. So we got negative 300, right? Then let me go ahead and calculate that value right there so it'll be easier for us to see. So we got X squared, 2 times 6 is 8, 6, 12, 200 divided by 12. Boom. So let's write this one right here as the value of 167 X squared pounds. That's what that is. That's our value right there. So negative 300 minus this entire resultant load, which is what it is, 1/2 base time height, minus 16.67 X squared. And then we got a V going down here. So we'll say minus V. And set that equal to 0. Set that equal to 0. Well, if we solve for V, we move things on their opposite side. We will find that V equal to negative 300. Matter of fact, let me write the variable in front. Is negative 16.67 squared minus 300. So guess what that is, y'all? That is showing V as a function of X. That's what we just did there. That's V. I scratched that out just to try to get it in that order, right? The way that we typically write it in calculus. Now let's do the moment. Let's sum the moment about the cut here. We're summing the moments about the cut. So we're going to sum the moment. We're going to use counterclockwise as our positive sign convention. And so the moment created by this 300 is going to be a positive 300 times X. Also, this distributed load is going to be creating a positive moment. So we'll say plus 16.67 X cubed. That's the force. But where would the resultant be? Where would the resultant be? Since this is triangular, it'd be 1/3 from the bottom. So the resultant of this will be right here, right? 1/3 for the bottom. So that distance here is X over 3, right? X over 3. So we're gonna write X over 3 right there. And then we have to include that M there. So we'll say plus M equals 0. So what do we do now? Well, we can isolate the M such that we can express the moment now as a function of X. 16.67, that's X cubed over 3 minus 300 X. Now check this out, right? Because of what I showed you already, if you were to take the derivative of this, you should get what? This. And sure enough, if you took the derivative of this, boom, boom, what would you get? You bring down that exponent, put it 2, those 3s to cancel out, you would get the Shear equation. Makes sense, makes sense. All right, last thing we need to do for this particular problem is that we need to plot, as it says, draw the shear moment diagrams. So I'm gonna go ahead and draw that for you so that you can know what it looks like. I think I might have enough room over here. Should I do it? Nah, I'm gonna flip it over. When I was in school, I had an issue of always trying to like cram stuff and like the smallest of crevices, and then they end up being illegible for the grader. So if we were to draw the shear diagram here, we're gonna start things off at whatever. Let me bring this over here so you can see this here. Our two-way cam. Boom, come back over here. We're going to start off knowing that this 300 is going to start us off at negative 300. So we're going to have a negative 300 here. Negative 300 pounds. Then it continues to go downward at a linear rate. So what that means is it starts off not as much of a slope, but it increases as it goes down. And then we know from when we saw for RA that this here should bring it back to 0. Why? Because RA was equal to a positive 900 pounds, and that positive 900 pounds will bring us back up here. So fairly simple. That is the diagram for our shear. What is the diagram for our moment? Well, we're going to do that just right below it so we can see some correspondence here. The moment at the very end, because it's cantilevered, internally it's not experiencing anything. It's going to start off at a 0. That's the moment. Then it's going to decrease at an even more aggressive slope than this one did. So it's going to come all the way down there. And this value should be exactly what the reactionary moment would be if we calculated it here for our overall structure. And I'm going to give that to you right now, just so you all will know it. You can go back and test your math skills there. Just do your equilibrium equation. But that value should be 3,000. This value is 0. And those units are pounds foot. So those are the shear and moment diagrams for this particular beam. Take a good look. The thing I really want to make sure y'all got was how we found these equations for shear moment as a function of X. Cool. We good to go. All right. I think I got another one of these actually. And I sure do. I sure do got another one of these printouts. And we're going to pull that over here right here for 6-6. So let's keep it moving with 6-6. I'll run through as many examples as I can today. And in this particular one, I can change the image up there in the corner, 6-6. It says to us, actually, I don't need that because it's on the paper. 6-6 says to us that draw the shear moment diagrams for the shaft. So we're going to draw shear moment diagrams just like we did in the last one. The bearings at A and B exert only vertical forces. So they're being very clear to let us know that these things here are only having vertical reactions. So we can go ahead and call that RA. We can call that RB. And then it says also express the shear moment in the shaft as a function of X within the region of 125 millimeters and 725 millimeters. So 125 plus 600, that means that they want us to find the equation for the X as they drawn on here that carries us into the center portion of a beam. So that's what we're going to look at today. That's what we're going to look at today. So first, let's go ahead and find our reactions. If you were to do sum the forces in the Y direction, right? And if you were to sum the moment, say about A, I'm just going to go ahead and cut to the chase and let you know that your RA, you all know how to do that, that's statics, your RA has a value of 815.63 newtons. And your RB has a value of 1484.38 newtons. All right, I encourage you to pause if you don't trust the math and see if your calculator concurs with mine. But those are the values we have right now. We have 815.63, and we have 1,484.38. But here's where the rubber meets the road, where we begin to get into our free body diagram. So let's draw this right here as if we were to cut it in the center portion, just like get access defined. All right, we're going to show our V going down, our moment going counterclockwise. Let's go ahead and apply our other forces on there. Hope everybody's staying healthy out there. I got a little sniffles over here myself. All right, so this is 815.63 newtons. Then slightly over here, 125 millimeters over, we got 800 newtons. Now, in order to solve for or to find the shear, we really can just go straight forward and solve for or sum the forces in the Y direction. And that tells us right here that 815, this one is pretty straightforward. 815.63 newtons minus 800 newtons. And then minus V, because it's going downward, equals 0. So the shear, right, as a function of X, now there's no X in it, but still nevertheless, it is basically a constant here. It is a constant of 15.63. That's pretty simple, right? Let's see if we can do the same thing for the moment. See if we can do the same thing for the moment. Now keep in mind that X is going this way, and that this distance right here is, in terms of meters, we're going to say 0.125. 0.125 meters. All right, so some of the forces in the, or some of the moments about the cut, we have a, again, we're calling this positive counterclockwise. So in this case, the 815 will be creating a negative moment, 815.63 times X. And then over here, this will be creating a positive 800 But what would be the distance? It's not X. It's not the full X, but it'll be whatever distance this is. Well, this distance is X minus 0.125 meters. So we're going to have 800 times X minus 0.125. And then, of course, we got plus M to account for that moment that's unknown. Let's solve for the moment here. In this case, if we distribute that through 800, 800x, this is 15 here, x. So we're going to see some things happen. We'll see some things happen right here. So this is going to simplify as M, 800 plus 800, 15, 800 plus 125. Ah, 100. Boom. So our value here is 15.63 x plus 100. So there we are. Our moment as a function of x. And this, though it's constant, is still answering the problem as shear as a function of x. There we have it. There we have it. All right. So now let's do what the problem is inevitably always going to ask us to do in these cases, and that is draw the shear moment diagram. And this is where I'm going to come out to this view here so you can keep your eye on it. So starting out here, we know that this reaction over here at RA was 815.63. I'm gonna round that up for the sake of the diagram to 816. So we're gonna go up here to 816. And then it's constant. It's constant. It goes over until it hits that first 800. So that first 800 is going to bring all the way down to 16. Makes sense? 16 newtons. So we had 816 newtons here. We rounded it just for the sake of making it clean. Then we come down here to 16. This is going to come all the way over to the other concentrated load, which is a negative 1500. Negative 1500 with a positive 16. That's going to bring us further down to now we have 1500 minus 16. So that's going to be a negative 1484 newtons. Well, does that check out? Does that check out? Y'all know how it wasn't static. Sometimes you do a shear moment diagram and then it doesn't go back to zero unless you know you did something wrong. Well, RB, according to RB, is 1484, and we rounded that up. So we're going to round that down. So that makes a lot of sense. This is our shear diagram. Boom. What is our moment diagram? Well, here's another way you can look at moment diagrams. Don't know if you knew this or not. But the moment diagram, again, is the integral. Moment is the integral or the antiderivative of V. So what we're starting off at 0, we're going to go up whatever area this is. So this right here was 0.125, remember? 0.125 meters. If we multiply 0.125 meters times 816, what is that going to give us? 0.1225 times 816. That's going to give us 102. So that means that this right here goes up to that point. It's going to line up with that point, which is 0.125 meters. And it's going to be the area under that, which is 102. 0.125 times 816. Then we're still on the positive side. So it's going to continue to go up the same amount of this area until it reaches another point up here. So we got 16 times, well, if you look at the diagram, that's 600 millimeters. So that's 0.6 meters. So 0.6 times 16, 16 times 0.6 is 9.6. So we're really going to add 9.6 onto this 102. So this goes all the way up to 111.6. That's what this is here. That's what this is right here. And then now we're below the axis. So this is going to go down whatever area this is, right? What's the area of that on there? 0.75 or 75 millimeters. So 0.075 meters. So 0.075 meters times 1484. Let's see what that is. 0.075 times 1484. 11 point. Look at that. It practically evens back out. Plus or minus there because, again, we did some rounding up here. But that's going to bring us back down to 0. And this, my friends, is the moment diagram. That is the shear diagram. And therefore, we have answered the call of first expressing shear moment within this region as a function of x, which is what we did here. And then we drew it as it said at the beginning of the problem statement. All right, cool. Makes sense. Makes sense. All right, let's keep this moving. Let's keep it moving. I'm gonna look at another one. I don't have a printout for it, but this is 6-10. And just to get us in the habit, of drawing shear moment diagrams. That's what this particular lecture is all about. I've showed you how to do it as a function of x. Keep that in mind. But I believe that this one may be a little bit more straightforward for us. Let me see if I can reposition this image in the top corner for us to be able to read it a little bit better. All right, cool. Hope y'all can see that. All right, so first things first, this is a bunch of concentrated loads. It tells us draw the shear moment diagrams. The bearings at A and D only exert vertical reactions on the shaft. So let me just go ahead and draw it like this. I do a shear or a free body diagram. We know that here at A, we got RA. Over here, we're going to have a downward force of 80 pounds. A little over, we're going to have another downward force of 110 pounds. And over here, we're going to draw another reaction. Call that RD. And then over here, we got another 35 pounds going down. 35 pounds, 80, 135. Let's just solve for our reactions. Let's do what we typically do in all these cases, right? So let's sum the moments around A. Looking at this, we got, calling that the positive direction. First things first, 14, this is going to create a negative. So let's say negative 14 inches times 80. This is going to cause another negative. So a negative 14 plus 20, which is 34. Make sure I say and write the same thing. 34 times 110. Next, we got this RD. That's going to create a positive. So we're going to have plus 14 plus 20 plus 15. So that is 49. 49 RD. And then we have also another negative. What's the full length? 14, 20, 15, 61. So negative 61 times 35. Running out of space here. Barely got it in. Set all that equal to 0. Now we're just solving for RD. If your math or your calculator or your algebra rather concurs with mine, your D in this case is going to come out to something like mathematically 6995 over 49, because that's the number we have there. And that's going to be equal to 142.76. Well, how do we solve for RA? We just sum the forces in the y direction. We know up is positive. So RA minus 80 minus 100, positive 142.76 minus 35 equals 0. RA in this case, if your calculator concurs with mine, should be 82.24 pounds. Boom. So that's RA, that's RD. Guys, I think we have enough in this case to go ahead and draw our shear diagram, right? We didn't really need to do it as a function of X. We can just draw the entire thing. So let me line it up right under our free body diagram. This is our shear diagram. RA is going to start off going up at 82.24. That's the value of RA. Then we're going to go down 80. So that's going to bring us down to 2.24. That's going to come over here to 100. We're going to go down 100. Let me round that a little bit for you. That's going to be about 100 and 107, if you will, a negative 107.76. Come over here and go up. RD is 142. So that's going to push us all the way up to roughly the 35 range, roughly 35. And that's going to come down. You'll find that these roundings are perfectly fine. Perfectly fine to round a little bit when you're drawing these diagrams. The main thing they want to see is that you're getting your shapes right and that your values are pretty much where they are. So if you round it, as long as you don't get anything egregious, like turn this into 90 or turn that into 5 or anything like that, you should be good. But you could have written that as a negative 108. That would have been just fine. That would have been just fine. Excuse me. So let's draw the moment diagram. Let's do it the same way that we did the others, where we just kind of looked at the areas. It's really easy to look at the areas. First here is 14, all right? I think that's what it is, 14 inches. 14 times 82.24. We can get that as, round it to be times 82.24. We can round that to 1151, right? We can say star 0 comes up here to 1151. Right, that's pretty much a line there. Now this value is here, this area is still above, so it's going to go up a little bit. So we're going to multiply that times the length of that, which is 20 inches. We should come up a little bit to about 196. Right, that's going to be in line here. Then we got this area below, so we're going to be dropping this pretty much below the axis. So let's just say 108 times whatever that is 15 inches here. 108 times 15 inches. 1620. Subtract from that. So subtract that. So bring this down to here. That's about a negative 420. So at negative 420, 35 times that last distance, 12. Of course, it should go back to 0, but just want to make sure. 420, boom, there it is. All right. Those are our shear moment diagrams for problem 610. Apologize. There you go. You can see the whole thing right there. I'll give you a second to take that all in. Now, what we're about to do right now is go ahead and do one more for the road. We'll do one more for the road. This one may get a little bit more tricky. This one is going to be problem 16 or 6-14. That's what we're going to look at right now, 6-14. Let me find the image for you so that you all can definitely follow along. There it is. All right. The instructions for these are very simple, y'all. It's not really asking us to do too much, but draw the shear and moment diagrams for the beam. That's all we got to do right now. Draw the shear moment diagram for the beam. But again, we're going to have to test ourselves a little bit to make sure we understand what is going on. So the first things first, let's go ahead and get our reactions to this thing. Let's get our reactions as we should. All right, so our reactions in this case, if we were to sum the, matter of fact, let me just draw the beam like this. I'll call this, since this is a B, I'll call it BY. I won't say RB. Really doesn't matter what you call it, RB, BY, same difference. Here is a intermediate support here, roller. I'll call that's an A, so AY. Obviously, we had our distributed load happening from the very end onto point A. This is 2 kips per foot. And then we have this little point here where there's a moment. You'll see exactly how we handle this in just a second. 30 kip per foot moment. Let's sum the forces. Well, I'll write the equation first of sum of the forces in the y direction. This distance is 2 times 5. So a negative 2 kips foot times 5 feet. Positive AY, positive BY. Any other vertical or y axis or y directional forces? Nope, there isn't. This is a moment, so we're not worrying about it in this case. So we can set that equal to 0. We can rearrange this to simply be AY plus BY equals 10. 10 kips. Next one, let's sum the moments about, let's say A, because we want to get rid of one of these unknowns so we can solve for both of these. Sum of the moments about A. 2 times 5 is 10 times the location or the distance of the resultant. Well, this is halfway through it. That's 5, so this should be 2.5. And that's going to create a positive moment. So we can say positive 10 times 2.5. We're not worrying about A. Now this is 30. Well, this 30 is a moment, obviously about that point, but it's still creating a negative moment. It's going the opposite direction. So we're going to say negative 30. Yes, that is 30 kip foot, if you want to go ahead and throw in the units. And then we're going to have a positive moment created by this BY. That's what we're doing there. So it's going to be, what's that distance from here to here? The diagram says that it is 10 feet. So 10 BY equals 0. What does that mean? That should mean that algebra all gives us the same value, which is BY is equal to 0.5 kips. And if BY is 0.5 kips, what does that make AY? Well, quite simple. It makes AY 9.5 kips. So far, so good. Everybody good? Okay. Let's go ahead and see if we can draw, just from inspection, our shear moment diagrams based on what we now have. I don't think we need to get the equations out for this. We could, in fact, if we were, we would say that this was X1. We would come over here and say, all right, between here and here would be X2. And then we could come over here and come all the way past and say that that's X3. But let's start things off, right? So we're starting at 0. There's no reaction at the very end. So this is 0. And then we're going to go down 10 in a linear fashion. So that's going to be down here. That's going to be negative 10. AY is 9.5. So that means that this should bring us up to just below the axis at a negative 0.5. And then this over here should bring us right over here to BY, which is 0. That's the shear diagram. Looks a little weird, but that's exactly what it is. That's exactly what it looks like. Let me shift up just a little bit to make sure you all can see what I do for the moment. Now, we have what we call here a localized moment. So that's going to cause an abrupt jump to take place at that point on the graph, on our moment graph. Not on our shear graph. We don't really see it on our shear graph because that's not a force. That's just a moment. But you'll see what we call here. We have a moment diagram. Hope that's coming in. All right, cool. Starting off at 0. This here is linear, so it's only going to increase. It is the area under that. So 1/2 base times height. So 1/2 5, 2.5 times 10. So it's going to come over here, and that's going to be a negative 25. Why? Because see, 1/2 that area. In case people haven't got what I was saying yet, I'm not going to pretend like everybody knew exactly what I'm saying. 1/2 base times height of this area, that triangular area, is equal to 2.5 times 10, 25. Just doing that just so people can know. So that's what brings us here to 25. Then we have, let's start with just looking at this part right here. 0.5 times the distance of half of that, which is 5. So 0.5 times 5 is 2.5. So this is going to increase from 25 in a linear fashion to negative 27.5. Then again, this is where our localized moment comes from. Our little moment right there is going to suddenly give us a negative, or not really a negative, but internally, since it's positive, it's going in this direction internally. It's going this way externally. Internally, it's going to be counteract that. So it's going to go from a negative 27 and it's going to jump up 30. It's going to jump up 30 to 2.5. And then the rest is just a rectangular. So it's a rectangle in the moment diagram, which means that it's going to be just a triangle and a rectangle in the shear diagram. So it's just going to be a triangle in the moment diagram. And that concludes how we draw our shear in our moment diagram for problem 614, problem 614. So I hope you all saw I did the harder ones actually, even though these were later numbers in the problem set. The harder ones were the first ones because we had to use our equations. We had to find it in terms of equations. But really, all in all, you want to make sure you have intuitive knack for drawing your shear moment diagrams. You want to make sure you are able to find the equations if you need to. But then also, it can be a very solid foundation of yours if you can just pull out your equilibrium equations, take a look at your free body diagram, and just have an intuitive sense for how to draw, or at least how they should look and shape. Well, I hope that helped you all. That concludes our lecture for today. We're going to continue on in chapter 6 in the next one. But until now, all the best on your assignments. Catch y'all later. Peace.